Let's talk about discontinuities. So f, a function f has a discontinuity at x. Okay, that means that is the same thing as saying that f is not continuous at x. Okay, we can also say that f is discontinuous. These are three ways of saying the same. Discontinuous. Let's move this more to the left at x. Okay, these are equivalent expressions. But what does it mean? If we remember from Calc 1, there is this notion of right-handed or left-handed limits. Okay. Here in this context, we are going to denote f of x plus. Okay. This is the limit, what is called the limit from the right. Okay. Is the limit as t tends to x from the right of f of t. Okay, and this, let's say this is a number q. Okay, so this is what I was calling the limit from the right. Okay, this plus here, the way to remember it is if we think about x equals 0. Okay, so x plus is whatever is on the right, on the plus side. Okay, so that's the trick to remember. But the actual definition is that f of tn converges to q as n tends to 0 for all sequences tn that are contained in the interval on the right of x. Okay, so let's call it xb. Here we are assuming that f is defined in some interval ab, let's say. Okay, and x is some point in the interval. Okay, x could be equal to a, so let's say that x is in the interval closed on the left a, open on the right b. Okay, now we can also define, of course, the limit from the left, which is f of x minus, is the limit as t approaches x from the left of ft, and it will be q, limit from the left. Okay, it will be q if f of tn converges to q as n converges to infinity. I wrote 0 before, but that's a mistake. For all sequences tn in ax. Okay, as before, f is defined in ab, and in this case x could be any number between a and then b closed on the right. I'm saying this may sound a little funny, but it's just in case we want the limit as x tends to b from the left of f of t, which is completely legitimate. Okay, with a picture, if we have our function here defined from a to b, okay, would be the limit as x tends to the right endpoint of the interval. Okay, now of course we say that there is a limit as t tends to x of f of t if these two half limits, these limits from the left and from the right, they both coincide. Okay, that's the definition of limit actually. Now, once we have this notation, we can classify the discontinuities. Okay, there are two types. The first are the discontinuities of the first kind, or simple discontinuities. Okay, and then we have, well, the second kind. Okay, in the first kind, we have that the lateral limits, the limits from the right and from the left, both exist. Okay, and the second kind is otherwise. That means that either of the limits doesn't exist or things like that. And then within the first kind, we have two possibilities. The first type is a jump discontinuity. Okay, this happens when if the limit from the right is different from the limit from the left. Okay, and then the function may or may not be defined at x. Okay, and that value could be equal to the limit, the lateral limits, or completely different. Okay, it could be equal to either of them or completely different from both of them. And then that's the jump discontinuity, and we have also removable discontinuities, which are when both lateral limits are equal, but they are different from the value of the function at the point. Okay, and then on top of this, we have infinite discontinuities. Okay, these happen when we have infinite limits, but we will see that later this week. Okay, so let's quickly with some graphs, let's see examples. For example, by what I mean by infinite discontinuity could be something like this. Okay, it has an asymptote, or it could be something like this. Okay. What I mean by a jump discontinuity, well, it's obvious. It's self-explanatory, right? It has a jump. Okay, but we see that actually the limit from either side exists. And then a removable discontinuity, well, it could be a very nice function, but suddenly it's missing a point. Okay, and at that point, the value is defined with a different value. Okay, so it's called removable because we could redefine the function by just shifting the outlier point and putting it, well, we could say where it belongs. Okay, making it match the lateral limits. Let's see some more complicated examples. For instance, we could have the function f of x that is 1 if x is a rational number and 0 if x is not a rational number, if it's irrational. Okay, so how is this function going to look? Well, we are not going to be able to tell. There will be the graph of the function would be both a line at height 1, but also at height 0. Okay, we'll have both of them because we cannot really for us it will look quite solid. Okay, we cannot tell that there are any missing points. Okay, because the rational numbers and the irrational numbers are both dense on R. Okay, but here is definitely an obstacle for continuity because this function has a discontinuity of the second kind uh, at every point. Okay, this is because the lateral limits do not exist for any point x. Okay, so let's say we have x here. Okay, we have sequences that converge to x such that f of tn converges to 1, but also different sequences, let's call them Sn, that converts to 0. Okay, so from the right or from the left, we can have different sequences. And this keeps oscillating. No matter how close we get to x, we will get infinitely many points that will give a value of 1 for the function, and infinitely many points that we will give a value of 0 for the function. We can even tweak a little bit this example and say, well, let's make it x if x is a rational number, and let's make it 0 if x is irrational. Okay, in this case, the function, again, is going to look very it's going to look like f of x equals x. Okay, but it will also be looking, let's plot it with a different color. It's going to be looking also like x, like f of x equals 0. Okay, this happens because, again, the rationals are dense on R and also the irrationals. So it will look, if we were to look at it, it will look like this is not a function at all, because we will see, it will look like it's not going to be able to pass the vertical line test because our eye is not able to tell the difference. Okay, but actually there is no problem because for its value, the value of f is perfectly determined. It's either x or 0, depending on if x is rational or not. But here we have a slightly different thing. So we have that 0 is a little special. Okay, because as we approach 0, it doesn't matter where we are coming from. The limit is always the same. Okay, so in this case, the function is continuous. At x equals 0. And it has a discontinuity of the second kind. Otherwise, let's say if x is different from 0. Okay, again here, the point is that the limit, if we take a sequence from the right or from the left, and we are converging to 0, then both x and 0 both are going to 0, okay? And we can have less wild things. Let's do a simple piecewise defined function, x plus 2, negative x minus 2, and x plus 2. And this is if x is between negative 3 and -2, -2, and 0, and 0, and 1. Okay, and in this case, this is actually much easier. So -2, we have the function x plus 2, okay, like this. And between -3 and -2, we have our function x right there. This is -2, this is -3, this is -2. So this is the second piece from -2 to 0, and then x plus 2 goes back here. And this is between 0 and 1. So we cut it off here. Say this is 1. Okay. And on the jump, we have that the value is 2. The value of the function is going to be 2. Okay, because the piece that matters is the last one. So here we have a discontinuity. If f is continuous at x in -3, 1, x different from 0, and f has a discontinuity of the first kind at 0, and this is a jump discontinuity. And finally, let's see one more example. The sine of 1 over x, 0. And sine of 1 over x, if x is different from 0, 0 otherwise. And this one looks perfectly fine. But if we graph it, we are going to see something's going on there. Okay, we can graph it quickly. Sine of 1 over x, there we go. So it starts oscillating faster and faster and faster and faster. But we are going to find a problem there, because clearly it doesn't matter what value we choose. Let me go back where I can write. Let's say we have our function that is oscillating between -1 and 1. Okay, and as it approaches 0, it becomes to oscillate very, very fast from both sides. Okay. Here the problem, the difficulty is that just pick a value and you will have a sequence, okay, that seems to converge to that value. But you can pick any value between -1 and 1, and you will get a sequence that converges to that value. So there can be no limit as x tends to 0 of 1 over x. Okay, this does not exist. For instance, just to make it more precise, we could take the sequence. Let's say x equals 1 over k pi. Okay, where k is plus or minus 1, plus or minus 2, and so on. Okay, the integers. Let's just say the integers. Okay, in this case, when I plug that value in, what I get is the sine of 1 over k pi, which is sine of k pi. Okay, and when I see that in the trigonometric circle, so it's going to be either here or here. So it's always going to be 0. So one could guess, well, okay, maybe the limit as x tends to 0 of f of x is 0 then. because it is for this sequence. But we could also take, let's say 2 divided by 2k plus 1 pi. Okay, again, k in z. These values, let's call them xk. Okay, xk converges to 0 again. And when I apply the function to these values xk, what I get is the sine of 2k plus 1 pi divided by 2, okay, which is either here or here. So it's going to be 1 or negative 1, depending on if k is even or odd. Okay, so in this case, it's even worse. Okay, in this case, the limit of xk does not exist itself for this sequence. Okay, so we see, and actually from the graph, we see that it's just a matter of choosing carefully the subsequence. We can get any limit between -1 and 1. Of course, in this case, f has a discontinuity of the second kind at x equals 0, and it's continuous otherwise.